All right, 3 laws of electrical charges. So in this, we're going to talk about 3 basic laws of electricity. We've talked about this already in class, but let's just dive a little bit deeper here. So in your notes in front of you, you're going to fill out this word in the first blank. Opposite charges attract. Thank you. Opposite charges attract. So if we have a positive charge, and the 2 types of charge would be positive and negative. If we have a positive charge and a negative charge brought near to each other, they would definitely attract each other, okay? If 2 objects attract each other like that, like amber and feathers, you can know that they have opposite charges. They are not going to be attracting each other if they're the same. So number 2, like charges or the same charges repel each other. So if you have 2 objects that are brought near to each other and they have the same charge, they will want to fly away from each other. And it doesn't matter if they're both positive or both negative. They will still experience the same repulsion. So the repel would be a verb. Repulsion would be a noun for, the state of things being repelled. Repulsion. Number 3, charged objects can attract neutral objects. Charged objects attract neutral. So even if we have one charged thing and we have a neutral object like this, there will be an attraction because, as we talked about the other day, the positives and negatives will line up, right? The positives and negatives will line up so that there would be a negative sort of side here. And so there will be an attraction between the positives here and the negatives here, okay? And even if it's oppositely charged, the neutral will line up in such a way that the particles will be able to kind of like partially be, this neutral object can be partially charged in the presence of another charged object. Okay. Any questions there about those 3 laws? Very important. Opposite charges attract, like charges repel, and charged objects can attract neutral objects. All right, we talked about lightning yesterday as well. A couple key points in your notes here is that lightning happens when there's a buildup of charge in the clouds, okay, due to the movement of the water particles and different things, the dust and the wind and all the different motions up there create static electricity. And the clouds would have a sort of a negative sort of end to the cloud and a positive end to the cloud. They would separate a bit. Sheet lightning would be, as we mentioned here, sheet lightning is a discharge within a big cloud. So sheet lightning would be discharge within a cloud. So if there's a negative and positive built up, sheet lightning would be discharge up in the clouds, within the cloud. There is lightning between cloud to cloud. And there's also lightning that would happen, or a discharge of electricity that would happen between clouds and the ground. So obviously, electrons, the negative regions in the cloud would want to, those would want to be balanced off. So there's lightning that would obviously come down to the ground. But also in the presence of, positive regions of charged space, the ground could actually become fairly negative, and lightning can go up into the clouds as well, actually. Lightning could go either way. I think, yeah, they all go off if you, we'll just leave it on. Yeah, these are just really small words for the app. I'll make it a bit bigger. Okay, any questions about lightning? We kind of talked about this the other day, but lightning. Okay, I think that's kind of interesting. The sheet lightning, when there's lots of cloud, right, and it's just like flashes within the cloud. It doesn't look like there's a bolt that comes down. That's sheet lightning, and that's static discharge between clouds. Do you guys have like on your bed? Would you have like fleece sheets at all? Fleece sheets, right? So if you have sheets that are really kind of soft and you know what fleece is, right? Like a fleece vest or a fleece jacket. So if you were to rub your sheets together, or even like move around in the night, or if you have like a sheet and then you have a fleece blanket on top, if you like pull those apart, like do this, in the dark, pull them apart, you can actually see discharge. You see little lightning in your bed there, lightning in between your blankets. And so that's kind of cool. That's just a small discharge of electricity. And with certain sheets and blankets, you'd be able to build up that charge a little bit better. If you have carpet in your room, right? things like that. You could rub your feet on the carpet, go walk around your room for half a minute or whatever, and then touch something, a metal lamp or something, you see you could make little lightning. Yeah. All right, next thing we're going to talk about is current electricity. Current electricity. So this is the kind of electricity we're most familiar with. We talked about static electricity, where it's just on objects and just the kind of the natural buildup of charge and release. But when we talk about current electricity, it's not like static in that current electricity is a flow. So when we talk about a flow of electrons or a flow of electricity, we're talking about current electricity. So current is sort of, we mentioned this is the word for the flow of electricity. So let's break this down a bit. So unlike static electricity, in current electricity, there's a continuous flow of electrons along the path. Okay? There's a continuous flow of electrons along the path. So here's a picture of a diagram of a battery. So here's a battery right up here. This is the battery. It's got a positive end and a negative end. So you know on batteries that there's a positive end and a negative end. You ever wonder what that means or what that represents? Well, the negative end has the source of electrons. That's the negative end where all the electrons are. And the electrons actually would move through a wire from the negative, and it would be attracted to what? To the positive end, you see? So it's coming back to the positive. So electrons are flowing this way. Electrons, okay? Electrons are flowing this way. Now, there is this strange sort of paradox here, and it's a little tough to explain. I don't know if I'll be explaining it much today, but even though we have electrons flowing one way, the current flow of electricity actually flows in the opposite direction. So when we talk about current and the flow of electricity, okay, lighting up a light bulb, let's say, okay, electrons flow one way from negative to positive, opposites attract, but the flow of current actually flows in the opposite direction. Okay, so the current flow is in the opposite direction. The electricity itself flows the opposite way. Yeah, that's strange, isn't it? The passage of electricity current through a material is referred to as conduction, or simply electricity. So we'll talk a little bit more about that here in a second. So the passage of electric current through a material is referred to as conduction, or simply electricity. So this is a little tough to explain here, guys, but the electrons, okay, think about these electrons that are moving one way, E, and this is a notation for electron. It's an E with a little bit of a negative as a exponent. So if the electrons are going one way, you can think about traditional current would be sort of like the positive charges that are like rushing in to replace the negative electron flow. And so the positive charges would be carrying the current. So they would be going this way. The positives are going this way. As electrons move this way, the positive parts sort of like replace that spot. They kind of fill in the spot where the electrons were. And it's actually the positive notion here, the positive that carries the current. So it's a little bit tough. Electrons go one way. The current that powers up lights and stuff like that goes the opposite way. Okay, let's take a look at electrical circuit, I mean. So we talked about circuit. That means the circuit is, that's the root of circle. And so it's a connection, right? It's a complete path. A circuit would be a complete path. There would be no breaks in the path. So in this electrical circuit, we have a battery, and we have a positive end and a negative end. The electrons are going one way, this way, right? The current is flowing the other way. So the actual power that powers things up would be going the other way. So there's a path, regardless, there's a path. And it has to be a closed path for the flow. If you think about this, let's say we have two cliffs here, okay? And there's a person walking, okay? And they're going in this direction. If they come to the cliff and this expanse is too big to jump, then they stop. And if there's a whole bunch of people that are also walking, right, then this flow of people has to stop here. That would be the same as if there was a break in the circuit. Okay? But if there's a bridge, here's a bridge, okay? There's a bridge that these people can walk across, then they will keep going. Right? They keep going across the bridge, and so on. And so this flow can continue. Question over there, girls? Question? No? I want you to understand what I'm saying. So whether you draw this on your diagram or not, it's up to you. Okay? You don't have to draw the stick man. Not necessarily. But an electrical circuit, okay? It's got to be closed. It has to be closed. Must. You might want to draw this, write this down. Must be closed, okay? There can be no gaps or spaces or else the current will flow. Must be a closed circuit. That means a full connection all the way around.
What if it was open? Would it like just escape it and then just out?
Well, if it's okay, if it's open, that means there would be no flow. If, let's say you have a battery here, and you have something like this, and here's your light bulb, and it's not connected at the other end, okay? All right, well, if these electrons, okay, or this positive, this current, shh, boys, you're not talking while I'm talking. Okay, you're not talking while I'm talking. I can hear what you're saying back there, okay? You guys will be moving right up here pretty quick, okay? So just please be quiet while I'm talking, all right? I don't want to talk over you. Question was asked, what happens if this is not closed? Okay, will they go somewhere else? If they can go somewhere else, they will. If they can't go somewhere else, then everything will stop. So if this is open, like this, if it's open, and it's not touching anywhere else, like there's not another, conductor that the end of this, let's say, wire would be touching, then it will be open, and that means the light would not light up, okay? If you had some kind of switch here, right? You think about an on-off switch for some electrical device that you have batteries for, like a light bulb, like a flashlight. Let's say this is a flashlight, okay? So here's the flashlight, all right? And you've got your light bulb on this end. Here's your big fat flashlight. And you got your on switch over here, okay? When it's off, the circuit or the path is open. There's no flow. When you turn it on, you close this so that the electrons now can flow, and then your light bulb lights up. Does that make sense?
Yeah.
Now, if you have a short, that means your switch is off. Oops. Your switch is off here, but somewhere else there's a break in the wire or something, and these electrons, or the power here, the positive power, I'll say this is the positive power, it's actually going somewhere else. It's going along a path somewhere else. It's made a connection somewhere else. It's called a short. So that means the light won't work. That also means that your battery will drain because there's no off. It's on all the time. And it's finding another path to get to the battery here or whatever. So that's not good. Or it's sucking the power, the current somewhere else. So that's what a short is in an electrical circuit. Okay? Now we're getting into a lot of different stuff. You guys are asking good questions and everything. Okay? But yeah, so a switch on off, open, closed, open, closed. Closed circuit, electrons flow, power flows, current flows. Open circuit, there's nowhere for it to go. It's like there's no bridge, so the people have to stop.
Can
Okay?
they not jump?
No, they can't jump.
Can't? Okay.
If there's somewhere where they could jump to keep going, that would be like a short, right?
Yeah.
If they're bypassing the bridge, or if there's no bridge and they somehow get over there, that would be like a short. You have a frayed wire or something, and it's connecting something else. So if this was in a car, right, and you have a bad wire and it's contacting some metal piece or the frame or something, then you have a short. Your light doesn't work, and your battery is draining. Bad news.
Yeah, that's what I was wondering.
Okay. All right, good. Let's keep going. Electrical current, an electrical current, so you want to put electrical in there, that's the word right there, will only flow if there is, as we said, a complete pathway through which the electrons can move. This pathway is called an electrical circuit. So what do you need for an electrical circuit? You need a source of electrical charges, which would generally be a battery or something like that, generating your electrical charge. You need a conducting path. So you need some kind of circuit for those charges to flow through. The switch that stops or starts the flow of electrons. In our previous diagram, we had a switch for our flashlight. And number 4, a device to use the electrical charge, referred to as the load. And in our diagram, of course, we had the light bulb as the load. Okay? All right. So I don't know if you guys have really looked too close at a light bulb before, a traditional light bulb. The LED bulbs are, this is not an LED bulb, this is a traditional light bulb. These ones are easy to kind of see what's happening here. So as the electricity flows through, and we won't worry about direction right now, but as the electricity flows through, comes in here, goes up here, and it flows through this coil, this metal coil, very, very thin, and then comes back and it keeps going on. Well, as it pushes through here, this little, it's called a filament, okay? It's called a filament, and it gets so, it's so thin, and there's so much kind of energy coming through that it glows really brightly. And little light bulbs, and the how they, light up a whole room, it comes from a tiny little filament, a tiny little piece of metal that the electricity, the power is running through, and it glows so white hot that it gives off light. So heat and light would be a byproduct of this electrical energy discharge. And so as the power comes through here, it kind of, some of the power gets used up here as heat and light, and then the flow continues on, and it has to go back to kind of its charging station, as the battery or the electricity, wherever the electricity is coming from. So it kind of uses a little bit of energy to do work, okay, or to power the load. So if you have an old style light bulb at home, you should have some at home, but there's a lot of the newer like LED bulbs and stuff like that are in a lot of homes now, even in my home, but I have some of these old ones. So take a look at it. And to check whether a light bulb was bad or not, you remember what you used to do?
Shake it.
Yeah, you shake it, and if you can hear this little piece of metal kind of bouncing around in there, inside the glass, then that means this filament has burnt out, or it's actually been separated, and so the electrons cannot flow through. It's not a closed circuit, the light bulb won't work. So when your old style light bulb goes out, it's usually because there's a problem here. This filament has actually been charged up so many times that it's burnt out and it's actually broken. And so it just kind of blows apart. And then we don't have a path anymore. Yeah, question? So if we think about voltage in batteries, okay, so what gives the power to maybe power this light bulb, or in our last example, right, this one right here, the flashlight, it's the voltage inside the battery. So the batteries, whether it's a 1.5 volt, the AA's, AAA's, or 1.5 volts. The rectangular sort of ones are the 9 volt batteries. Some of the big ones are, so that's where the power comes from, and it's from chemical reactions inside the battery. And we'll talk a little bit more about the battery and we'll talk a little bit more about how that energy kind of gets created. Okay. So examples of everyday loads, as we talked about light bulbs, here's that space heater that I was thinking of before, the space heater right here. So if you have energy, electricity coming through here, it lights these things up. Remember, when energy is used up, when energy is used, it provides heat and light, right? And so some things are good at providing just light and not a lot of heat. Some things are good at producing a lot of heat and not a lot of light. So this electricity is being pushed really hard through here, and it's basically all the little atoms in this material are getting very, very agitated and vibrating and creating a lot of heat. And so that heat is being displaced out into the air here. I talked about little appliances, right? Your blender or a coffee maker, or your kettle at home, or little toys that you put batteries in, right? You turn them on or whatever, electric cars or things like that. Loads, okay? Examples of everyday loads. All right. Let's finish off with this. I think we have just a couple pages left here for our notes. So let's finish these off. Open and closed circuits. Talked a little bit about this already. Let's formalize this here. There are 2 types of circuits.
Small box.
This is really small, guys. Yeah, in your notes. Sorry. You might have to just write these beside. I don't know. Yeah, it's hard to read, actually. Open circuits are formed when the flow of electrons is interrupted and they can no longer move past a certain point. So and here's the diagram below that you're going to draw on your paper there. Okay. An open circuit would be this one on the left. An open circuit, we would have some kind of power source, some kind of load, light bulb here. And then we would have an open space here. So this would be a switch being opened or some kind of disconnection in the path. So there's nothing happening here. The electricity is not flowing. There's no power flowing. That's an open circuit. The closed circuits are formed when there is a continuous flow of electrons. So the closed circuit over here on the right, let me that yellow, closed. You'd have your power source, you'd have your path, you'd have your load, and there is no disruption, no interruption of the path. This would be a complete path, okay? The electrons are flowing and they're giving off some energy. They come back to the battery, get kind of charged up again. There's chemical reactions happening in batteries, and we'll talk more about batteries, but that chemical reaction provides kind of excess electrons to be moving, and it's these chemical reactions inside the battery that that provide our energy. Hand, yes.
What would happen if, like,
Okay, just as we finish this video here, a person can use a simple device called a current detector. A current detector to determine whether a circuit is open or closed. And this is an example of a current detector that you'll see that some electricians might have. I have one of these at home as well. So if you want to see that if there is electricity flowing by a point, you basically touch this end here to the wire or near the wire, and this light on this end will light up. So it'll detect the current. So a current detector detects whether or not current electricity is running through a device. The shortcoming of such a device is that it's not able to measure the amount, just whether some current is present. All right. So as we mentioned here, if you're an electrician and you want to know if this wire is hot, they say it's hot. If there's electricity flowing through it, they bring this close, and if it goes beep, 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 and lights up, then you know there is electricity there. And they know not to cut it then and to do their work on it. So they want to detect to see if there's electricity flowing for safety reasons and things like that. Okay, so that wraps up our little lesson on open, closed circuits, loads, paths, current electricity, and the three laws.